Determine whether the integral between 2 and infinity, so we have an improper interval, 1 over the square root of x minus 1 dx with respect to x, determine whether that is convergent or divergent. So it's not asking us to evaluate the integral. We don't need to try and get a number. We just need to say, does it converge or diverge? So what we are going to do is use the comparison test. The comparison test, the aim is you get an f of x and a g of x such that for the interval that you're looking at it over, so in this case we're looking at improper intervals, so we're looking at x being greater than or equal to a. Remember, that's the lower limit of the improper integral, the upper limit being infinity. So if we can get a situation like this, so that this is true, that your f of x is greater than or equal to 0, so it's positive, but it's less than another g of x for all of these x's that are greater than or equal to your lower limits. If you can get a situation like that, then the comparison test says that if the smaller one, so if the integral between a and infinity of f of x dx, if the small one diverges, so will the big one. G of x dx, that will also diverge, right? And it follows that if the smaller, so if the bigger function g of x, so if the integral between a and infinity of the larger function g of x dx, if that converges, then so will the smaller one, so the integral of f of x gx between dx, between these same limits, that will also converge. That's the only conclusive part. So basically, if the small one converges, that doesn't tell you anything, and if the large one diverges, it's all about bounding really. What we're going to do, we're going to show that this will diverge, and we're going to try and use our new information about a p-series. So what we're going to do, we know that x is greater than or equal to 2 because our lower limit of the integral is 2. So basically, the square root of x minus 1 is going to be less than or equal to the square root of x for all x greater than or equal to 2, and also because the square root of 2 is about 1.4-ish, so that's square root of 2 minus 1 will also be positive, so that's a good start. It's not quite what we're after because we're looking for the reciprocal, so now we need to consider, well, if we take reciprocals of both of these, what would happen? So if this number is bigger than that, if the square root of x is bigger than the square root of x minus 1, then the reciprocal of the bigger number will be smaller than the reciprocal of the smaller number, right? So that means 1 over the square root of x, because the square root of x was a bigger number, well, that's going to be less than or equal to 1 over the square root of x minus 1, right? But because we know that x is greater than or equal to 2, these numbers in the bottom are always positive, so everything's positive, so this is still greater than or equal to 0. So now we've got our 0, we've got our f of x, which is this one, and we've got our g of x, which is actually the function that we're interested in. So we are finding the integral between 2 and infinity of 1 over root x minus 1 dx, so it's this one, right? So now what we can do, if we can show that the small one diverges, then it will prove that this diverges because this situation is true, right? So the integral between 2 and infinity of 1 over root x dx, right? We're looking to make this into a p-series. To use a p-series argument, you need this lower limit to be 1. Remember, the p-series says that it's interested in 1 over x to the p, the integral of 1 over x to the p dx between 1 and infinity. So to make that the case, well, we need to say, well, this is the integral between 1 and infinity of 1 over root x dx, and then we're going to have to remove the 2, 1 part, so minus the integral between 1 and 2 of 1 over root x dx, just like that, right? Now, if you look at that, if we just look at this bit and just think about it, this is an integral that we could evaluate. We're not going to, so this is a definite integral. Definite integral that converges, right? We could, if we wanted to, we could evaluate that using what we know about integration, put the limits in, and we could get a number. If it equals an actual number, it obviously converges, right? This bit here, this is a p-series, right? So this bit here is the integral between 1 and infinity of, well, it's 1 over x to the 0.5, right? dx. So this is a p-series. P-series with p is less than or equal to 1. And when you get a p-series with p less than or equal to 1, that means it diverges. Integral diverges. Okay, so if this part of the integral diverges, then the whole integral diverges, right? So that means that the integral between 2 and infinity of 1 over root x dx, it means that that diverges, which in turn means that the integral between 2 and infinity of 1 over the square root of x minus 1 with respect to x also diverges. And we must state the reason why, and the reason is comparison test. So what we've done, we've got to situate, we've found a function to compare it to that is positive for all the x's that we're interested in, which were 2 and upwards. This function is positive, but it gives smaller values than the function we're interested in. It's always going to be underneath, right? So as the conditions for the comparison test is set, if the small one that's underneath diverges, then the bigger one must also diverge, because if you think about it, if it's a smaller function and that diverges, well, how could the other one not diverge?